Good afternoon, good morning, and good evening. We welcome you all. Thanks for taking time to join for this meeting. And we welcome you all and very glad to start our first India Bioimaging webinar session. Just before we start the webinar, I'll just going to take 2 minutes to introduce who we are. We are India Bioimaging community, which we are growing, and it started in 2012, and it was in hibernate mode for a while, and now we are trying to get it back with a lot of volunteers from different institutes in India, and we have a few institutes, and as a part of it, as a partner, we had our first inaugural meeting of India Bioimaging in December 2024, where 32 institutes and imaging facilities across India had joined the meeting, and we had our own objectives and goals. These are the few objectives that we are starting with, and trying to do this and trying to give access to the microscopy facilities that are. And in the meanwhile, we are also as a team trying to ensure that we can self-sustain as a community, as a consortium soon. And this is a growing community, and through the help of volunteers from different parts of the institutes, I sincerely thank all of them to take part to be on this. So we welcome any of the students or any imaging facility across the nation can reach out to us. And we have not only the Indian partners, we have also the global partners and the corporate partners, which supports IBI. And we have formed a couple of working group after our inauguration meeting, and we have the formal co-chairs for India Bioimaging, Dr. Jamuna, Dr. Venkatesan, and Dr. Santosh from different institutes. And we have our advisors on board. With their help, we are trying to grow and form small working groups as an outreach and for training programs and so on. And who are new and hearing for the first time about India Bioimaging, please do visit our webpage. We launched our webpage in March 2025. We are on the social medias as well. And this is a small training group. Our goal is to come up with the training programs which is unified for everybody. These are upcoming courses. Please, for more details, please visit the India Bioimaging webpage. And our next first annual meeting is going to happen in December 2025. Please, if you are part of a facility or a student and who has an interest, please, you can go ahead for the details and register for the meeting. So with this, of course, as I said, this is we do face challenges. We all are the volunteers who are pushing this and trying to move forward. We are all doing with our passion as a big strength for all of us, and I hope we get a lot of volunteers more, and we hope to keep growing. Thank you. And I would stop here, and Dr. Sudipta can share the screen. So Dr. Sudipta, who is a senior professor in the BITS Pilani, Hyderabad currently, and but he had started his career in IIT Kanpur and has done his PhD in biophysics from University of Pennsylvania and postdoctoral research on Cornell University. And his research starts from, current research interests are biophysics and neurotransmission, membrane modulation, and I can keep on increasing the list. And he is one of the pioneer person in microscopy, as far as I know, in the biophysics field. And he has recently going to exploring a new kind of avenue, I think, in BITS, and trying to come up with a AI-based diagnostic tool. And I think we are going to have more fun in hearing Dr. Sudipta. So, I mean, I warmly welcome you. The stage is yours. Please go ahead.
Thank you very much, Lakshmi. And thanks a lot to the whole India bioimaging team. I think it's absolutely needed that we actually cooperate with each other with whatever resources we have, not just for the economy of the thing, economy of the scale, but also for exchanging ideas. I mean, when somebody is trying to buy a microscope, he or she needs to know, what is it for? What is it going to be used for? How much should it cost? What other extra things that he or she might need? What is there at the other end of the city? And these are things that require, because microscopes are getting extremely expensive day by day. These are things together in a country such as ours, so where the resources are limited, we can go very far ahead. We actually started our tool building in microscopy workshop in 2009. So we should hold hands with IBI. We have a Fluorescence Society, more of a scientist and technical aspects of it, not the biological aspect. So I think it's a perfect match. So I'll keep talking to you, Lakshmi, and your Nahit and Sugarna and others. And fantastic too. I heard about your setting up, but then I lost track. And thanks a lot for the introduction. So what I wanted to do today is actually give a bit of an introduction, exactly what I talked about. Things are getting expensive, but you should know what you want, what you need it for, and you may not need it. Okay, so let me start with that, with a little experiment. Okay, and for the little experiment, maybe I can still use my can you see it? Okay,
yes.
Focus. Okay, so maybe I will change over to as I talk. I will change over to the phone. I will unshare this. We'll run a little experiment. Basically, giving the idea what is a microscopy for, what is fluorescence microscopy, and all the complications that I will talk about. Where do they originate? Where is the problem that we are trying to solve? And of course, there are multiple problems, multiple parameters that you want to optimize. But let's just get a feel of that. What you see on the screen itself is an introduction to the problem. You have multiple objects, and you can see them very well when they're macroscopic, as on the top. And then, of course, if they're smaller, it's a little more difficult to see. As you go further and further down that arrow, they get smaller and smaller. It's the same object. It's just now part of the microscopic world. Well, in this, the milliscopic world, let's say, and it gets difficult to see. I want to see, as a general problem in imaging, is any object can be modeled as a bunch of points which can have different characteristics, but they're visible in some way or the other. So these are the bunch of points at the top, and the same bunch of points are at the bottom, but I can't tell what the things are at that point, C or YFP or something. And you want to look at that, and there is a way to differentiate this. Okay, that same thing that we do when you have a performance going on in a theater. There is a spotlight that comes in, and you see the dancer that the director wants you to see. Similarly, you put a spotlight on, but that's not good enough. So there is illumination, which is the first part of microscopy, but you need to image it onto a detector, and the detector also has to discriminate. So the illumination, when I do an illumination of something which is very particular, that absorbs at a particular wavelength and emits at a particular wavelength, then I put in that color. Okay, it could be you would say, why not a flashlight? I have a flashlight in here. The reason that it's not a flashlight is because I need to focus. It's a microscopic world, and your laser can be focused to the smallest point, much smaller point than a flashlight can be focused with. So we use a laser of the right color that will get absorbed by one type of the object. Here, the type of the object was the red object that I showed over there in that little experiment. And then it absorbs light and it emits a color. And you have to, so the red color actually emits, it absorbs green. That's the laser that Kuldeep had. And it emits orange light. So if we had no filter on it, no filter on my detector, it will be just too bright and you won't see any specific information. So you put a filter on the detector side so that what it's emitting, the emission color, is coming into your detector and nothing else. And that way, occasionally when you was, for those who had seen it, occasionally when you're scanning it, things are flashing. It's exactly how a confocal microscope works. Okay, you scan your sample with a laser. The specific molecules you want to see, you already know which molecule you want to see. The laser color is absorbed by them, and it gets imaged onto your detector through a filter. This part almost everybody here would know and understand. But let me ask. So as we go through it, I'll ask, what exactly do you want to see? This is a question that all of you, whoever does microscopy, and some of you are facility managers, whoever comes up to you and says, oh, I want to look at this sample, I want your best microscope. There's no best microscope. There are horses for courses. There are microscopes which will do the job much better than a more expensive microscope if the problem warrants it. So it's not like the better or the more expensive microscope is always better. There was a problem that I faced many times when I taught the Bangalore microscopy course in MCBS and in other places. People need to understand what they need to optimize. So I put in about half a dozen things here that we typically try to optimize. First, of course, is resolution. I want to look at it smaller. Of course, you don't need resolution which is more than what you want to see. You want to see just mitochondria swimming around, you just need a normal, what you call normal confocal resolution. You want to see nuclear pores, then you want a nanometric resolution. So you need to know what you're trying to look at. But that's the basic of microscopy, as the name suggests. And we can go all the way to the modern behemoths, the MinFlux. I'll tell you a little bit about it, and go down to 1 nanometer level. But it comes with its baggage. So you have to know what you're looking for and whether that's something that you. So we'll talk about resolution, we'll talk about speed, we'll talk about other parameters than just the brightness, spectrum, lifetime. They're all contrast agents that can make your molecule stand out against the background. Of course, sensitivity is an issue that is almost as important as resolution in any microscope. Molecular specificity, as I just showed, with a green laser, we could look at spots which are made with orange color, fluorescent color. So molecules have to be painted in some way. In fact, the GAP got a Nobel Prize in 2008. 4 people invented it. Unfortunately, only 3 got the Nobel Prize. But it is a way of painting inside the cell. And the challenge has been for a very long time. If you have to paint, you have to alter your system somehow. Can we not go without painting? And I'll talk a little bit about that. And then finally is, anything, even light, which is the mildest, one of the mildest things, still perturbs what you're imaging, especially if it's a live thing, especially if it's a live brain, especially if it's in vivo. Okay, so you want to put it as little light as possible. There's some exciting new possibilities with quantum light with entangled photons that I'll have a slide on if I have the time. So exactly how much more time do I have? Can you tell me, Nihit or Lakshmi? Somebody? You guys are...
We planned it until 4 p.m. But yeah, we thought we'll have like 45 minutes of lecture and then followed by 15 minutes of question sessions. But you can plan it accordingly too. If you have more things to share, probably the question sessions can be shortened as well, Dr. Sudipta.
Okay. Can I request, since it's already 3:25, can I request at least half an hour for the lecture so that roughly about 4 I will stop and then the question answers can go on, because we started a little late and we got a little mixed up in the experiment. Sorry about that. Okay, so I'll start. My hard stop is at 4. Okay, my lecture. Okay, so the things which are under yellow are the things that we have worked on ourselves. Of course, India hasn't really invented many microscopes or any, so to say. Some methods, some of us have invented, and we need to do a lot more with it. So this right side, which is under the yellow highlight, are things that we are working on. And any of you who want to work on this or want to join hands working on this, I'll be delighted to do that. But this is sort of our efforts to do something. So these are the areas where you have made some contribution. Left are things that I will talk about, but okay, so let's start. So to do those 6 things, to optimize those, you have only 4 handles. You have illumination, you have the object, the object needs to be painted, so the object is important. You have the detection, and you have analysis, post-processing. And with AI, it's becoming, machine learning is becoming more and more important. But you only have these 4 things to play with. Let's see how we play with this. Okay. Let's first go to resolution and start in a historical. But though I say historical, confocal is still the bread and butter thing for most imaging facilities all over the world, not just in India. Let's talk about confocal a little bit, and that will tell us where the basic limits of microscopy come from. The basic limit comes from the fact that if I had those very, very small objects, and you would say that if I could make an extremely small focus point, then if I could scan it one by one, I could actually get data no matter how small the object is. So therefore, I should have infinite resolution to the extent I can. I should be, to the extent I can make my illumination point very small. There is a problem, and the point is the illumination point cannot be made very small. It has a physical limit. It's called the diffraction limit. So all light, no matter how good a lens you have, can only be focused to a thing like this quantity at the bottom, 0.6 lambda over Na. You can see it, 0.6 lambda over Na. So I'll just have a pointer here. So here, lambda is the wavelength that you're using, and Na is the lens. Lens Na is defined as the refractive index N times sine of this angle. So the sharper the angle that the lens can make, the higher the resolution is, but it's a sine of a quantity, and sine can only be as big as 1. So if refractive index is, let's say, is air, then you can have Na, even theoretically, only 1. So 0.6 lambda is your limit. Okay, so if, of course, you go to water or oil, the N of the N sine alpha gives you a little advantage. In oil, 1.5, but you are always within lambda by 2. You cannot focus your light more than that. So that's the fundamental limit of resolution. Given the lambda typically invisible is 500 nanometers, we take the resolution limit to be about 250 nanometers, 0.25 microns. Okay? I'll come to the Nobel Prize winning discoveries that I would not say have broken the limit, but have gone around it. But first, confocal, because most of our devices, on one way or the other, relate to confocal. The confocal, what it did is put something on the detection side. In the excitation side, you take a laser because it can be pointed to the smallest point, which is that 0.6 lambda over Na. But then you have a wide distribution. So there is an intensity as a function of distance from the focus center. So you see that there are these rings. These rings you can see here. If you plot them across like this, the plot will be something like that. And inside that 0.6 lambda over Na circle is there. First thing you need to do is to cut off these outside rings, and that you use a detection pinhole. This pinhole can be moved around. I have put it deliberately off center, but you should center it. And then you'll get detection of only the central part. And I'm showing it in 2D. There is also resolution in, slicing in 3D. And that's what confocal does. And this idea is now more than 70 years old, but it really became commercial with when this man designed something and Bio-Rad commercialized it, Brad Amos. And so in the 80s, this beast called confocal microscope started coming into the biologist lab. And before that, the biologists didn't have much to do with lasers. Okay, and so this is the device, puts a pinhole, does the microscopy, and the modern device you can see on the right, it's I'm no particular fan of any particular company, but there's a Leica, I think a Stellaris, and there's an image taken by the Stellaris. So you can record beautiful images in multiple colors because you have multiple lasers and you can go. Okay. So it's still very much within the limit 0.6 lambda over Na, or roughly lambda by 2. Now what? So that has been the limit that has been known for 200 years, and we needed to, or 150 years, and we needed to go beyond. So this is the first thing that I'll talk properly about. It's a STED microscope. Some of you know about it. Some of you may have it in your facilities. Some of you may. Okay, this goes around that lambda/2 resolution by using both the illumination scheme and the object. As I said, you have only 4 things to talk about, to play with, 4 handles. So the illumination is a donut, in a donut shape. And the idea is the donut is actually a silencer beam. There is an excitation right at the center, again lambda/2, and you have a donut which goes around the center, but not at the center, and drops the excited molecules down in a color which is different from the color that is in front of your detector, the filter in front of your detector. Your detector doesn't see them going down, so it sort of looks dark. And the molecules will be saturable, and most fluorophores are saturable. So as you increase the intensity of the donut, mind you, the donut, if I took a cross section like this, to still be given by the lambda/2 in a different way. But if you intensify the STED beam, the saturation happens so that nothing more can be done here, but things can be done at the edge of this edge. So the donut sort of expands and starts filling up the center. So you have this kind of initially this kind of profile, and your center is the non-silence part. You can see it, but as you increase the donut strength, this is your saturation level. You see that what is left after silencing is getting smaller and smaller. Initially, you have the full lambda/2, and at the end, after you have gone to that intensity, you have this. And theoretically, there is no limit. If you can dump enormous amount of power, you'll get down to as small an area that you want, which is not silenced, because at the center of the donut, there is a real zero. So nothing will get silenced at the real zero. This idea came to Stefan Hell, who won Nobel Prize for it. And this donut-shaped silencer, as I have shown it here, ultimately all the things around it, except for the guy at the center, would be fluorescent. And you image it, and you know that it's coming from usually a sub-20 nanometer area. But as I said, there is no theoretical. Again, does not break the diffraction barrier. It is the object which gets saturated, therefore you get the shape, which is non-classical optics. And you can do marvelous things with it. This is 20 years ago, and this is what is now possible, showing I think the cytoskeletal network inside the new. Okay, so point is that these are the new things that have come up. You have technically broken the diffraction barrier, though not practically, using one of those. And you, as a user of microscopy or a facility manager, should remember those 4 things. Those are all the only things you can play with. Now let's go to both resolution and sensitivity. I'll talk about TIFR microscopy, total internal reflection fluorescence microscope. Till now, we're talking about very high intensity beams. I'm talking about now very low intensity beams. Okay, a TIFR microscope is easy to build, and we have built many over the years. And what happens is that you have the excitation. What it does, it doesn't go point by point and scan your sample. It illuminates an area. Illuminates an area right on top of the cover slip on which your sample is. And it can, the way that it works, it can only see about 100 nanometers above the cover slip, not beyond. It has 2 advantages and a disadvantage. Let me first tell you how it does it. And you come in with a beam which is oblique. So it comes from the side of the objective, so it becomes oblique. So oblique, then when it meets the water on top of the cover slip, it's going from glass to water, and water is lower refractive index. All of you will remember there is something called total internal reflection, and that happens when you go from denser medium to lighter medium optically. It gets total internally reflected. No light comes out. You see here, the light goes in, light goes out, goes back out. Sample is here. So sample doesn't get excited, except there is something called, and it is still classical, something called evanescent field. The light cannot suddenly turn back. It illuminates a little bit, but the light doesn't escape. Everything comes back. but it illuminates a little bit above the cover slip. And so any molecule which is fluorescent above that can get excited and give you fluorescence. It's great because you don't have the whole background from all the other molecules. A few molecules which is very close are stuck to your cover slip, you can see. This is an actual image of single molecules of amyloid beta peptide, which is responsible for Alzheimer's. You can see individuals. I'll come back to this and ask you questions. You see individuals, some are a little brighter than the others. And actually, there is a lot of science in there. But as of now, I'm telling you, single molecules, some can be dimers or trimers. Okay. And that's a research question that we are asking. I'll come back. Okay, so this is a very low level because you don't need any dumping beam like the STED or something. And it's also reasonably fast because you are illuminating the whole area, all that your objective can collect from, and you take one shot image. You have a camera which records everything. Instead of scanning along a point which takes time, you do one shot image. So it's reasonably fast, because it's sort of a sheet of light right on top of the covers. Okay, and it has very high sensitivity. It can see single molecules. That's the best you can do. You can see single molecules. Now, what is the resolution? The resolution is the same, lambda/2. Each spot of molecule will be, if you zoom up on this, you will see that they're spread out. The molecule is small, but the image will look like it's 250 nanometers. Okay. This man, Eric Betzig, worked a way around it to get to super resolution. Super resolution, the term always means that I'm going below the diffraction limit, going much below lambda/2. So again, he used the object. So he took GAP molecules to label the proteins, which can be photochemically silenced. So there you excite them, they go to a different energy state, comes down to a state where they're silent, they're not fluorescent anymore. The good thing is that individual molecules, if you have them sparse on your cover slip, you can see them separately. The point he made, and other people have made before it, if I can see individual molecules, even though it's 250 nanometers, I can plot a curve which will tell me where the center of that 250 nanometer is, and the molecule must be there. Because it's something that slowly becomes fuzzy and the brightest at the center. So it should be easy to pick up the center. Even though the whole circle is 250 nanometers, you should be able to pick up the center. That's true. But the problem is there's another molecule right next to it and 5 nanometers away. It has its own 250 nanometer circle around it, another one, and they're all overlapping. So you can never see a single molecule like that. Except if you could silence them. STED silence. This silences it another way. STED silenced an area. Didn't care about single molecules or 10 molecules or 1,000 molecules. Here is molecule by molecule. You silence them and then wake them up with another photochemical conversion in a sparse way, so that you have 5 molecules within your 250 nanometer, but at most one wakes up. So you image that, then you bleach it. So you keep imaging until it's bleached. So that guy can never be woken up again. That's dead. And you wake up another one. And another one. So you do multiple scanning and you can build up your statistics, those airy disks for each molecule, record it in your computer, assign the center, and you have built up a molecular level image, which again theoretically has no resolution limit. It's really statistics. Okay. So you see on the right something which is conventional microscopy and something which is done with single molecule microscopy. Is photoactivatable light microscopy. There are many variants of it now, and you can buy a TIFR machine and you can put in the appropriate algorithms. You can do this. There should be activation lasers, etc., and you can do this. So Stefan Hell and Eric Betzig both got their Nobel Prizes together in 2014 by doing this. Okay, by breaking, quote unquote, breaking the diffraction barrier. So a new era has dawned on us. Resolution is no longer limited by anything physical. Okay, the latest thing, and that I will talk to you about, is a MinFlux. You may have heard about MinFlux. Maybe 1 or 2 MinFluxes have come to India, though I haven't heard of one. Maybe, no, I think NCBS has one. But anyway, most people would not have access to it. But most people should not even rue its absence, because it's very a specific beast for very specific applications. Not all samples can benefit from. The MILFlux is a combination of these donut-shaped beam and photoactivation. By photoactivation, you silence everything except perhaps one. And instead of the donut-shaped beam being a silencer, photophysical silencer, this is now the exciter. So you excite it. So suppose you have a molecule right here. So if you put a donut, that orange molecule is visible. It emits some light. But you move your donut so that that orange molecule comes to the center. And if it comes to the center, there is no more any excitation light. So it's dark because it's at a dark spot. And you try to focus and guess where that center is. If you come close to the molecule, it excites again, and you see some fluorescence. You say, no, come back, move my donut so that it's at the center, we can't see it. So I sort of say it is there by not seeing it. Because if I move my donut, it will get into the illuminated area of the donut and it'll start seeing some photon. The good thing about it is that you're not exciting the actual molecule that you're localizing. So the molecule survives for a very, very long time, and you can do a very precise determination of its location, frequently below a nanometer. It is high resolution, but it's slow. It does it molecule by molecule, takes a few microseconds for each molecule, which if you have a billion molecules, it's a lot of billion microseconds. And it's not for all samples. You have to have special dyes which would be responding well so that you can do it. But for the samples it works, it's marvelous. Okay. So now I go to speed. So I talked about resolution. And I'll take questions at the end. Typically, at this point, I'll ask questions, but ask people to ask questions, but we'll go to the next thing. Okay? A breather. Whatever we talked about, resolution. The most important thing in microscopy. Resolution, typically, even with a confocal, is lambda/2, lambda being the wavelength you're using. But with STED, with PALM, or with MINFlux, you can go much below lambda/2. So 10 nanometer light imaging now has become routine, but everything has its own. So why does confocal still survive? Because at the speed, at the thing, it's not just a cost. Most experiments don't need 10 nanometers. Okay, if you do need it, then you'll have to take one of these. Okay, all right. Let's come to speed, because I just say that confocal itself is slow because it does point-by-point scanning. But if you can have a sheet, such as you can do in TIFR microscopy, it can be faster because the whole sheet is recorded on imaged on a camera at one shot. So this idea has been there for a very long time, but the modern times, Ernst Stelzer came up with the idea that I want a sheet. I say, okay, TIFR gives you a sheet. But remember, TIFR gives you a sheet only on top of the cover slip. It doesn't look anywhere else, cannot look anywhere else. So Ernst came up with the idea that, okay, you put a lens, a cylindrical kind of lens. So you actually make a sheet of light and move that, either your sample through that sheet of light or move your sheet of light through the sample. So it's not as good as TIFR because TIFR, due to evanescent field, is extremely high resolution in the Z direction, in the depth direction. It's less than 100 nanometers. This will be typically 2-3 microns. But if you're looking at large objects, which are already hundreds of microns, you don't really care about 100 nanometers. You want to do it fast. And this can be done fast because it retains the advantage of TIFR, one shot, whole area. So wide field is like this, confocal is at a point, multiphoton I'll talk about, 2-photon is also a point. Total internal reflection is the sheet, but right at the bottom, and the light sheet can be moved up and down, and you can do microscopy using a geometry which you can see on the right with a sheet created. The object is typically kept like this and rotated so that you get different planes through the object, and this is the collection. And this geometry has one disadvantage. It's very difficult to pick up with a high numerical aperture objective, which gives you high resolution, because two microscope objectives have to get their noses together. And noses together means they can at most be 45 degrees. And that means it's a low NA objective, a relatively low NA objective. That's a problem it has. Typically, you don't have very high resolution. There are newer inventions with lattice light sheet, etc., which can go to higher resolution, but typical light sheet would not have. but Zeiss, and some of you would have a Zeiss light sheet or other Leica light sheet microscope. And it does, again, for the stuff that you want an embryo to be imaged in a scale of a second or a few seconds, this is the only way you can go. So horses for courses. So the last 15 minutes, let me focus on things that we have had some we have made some contributions to. So other parameters, okay, other parameters means it's not color or brightness. There are other parameters such as the whole spectrum, lifetime. Lifetime is how long a molecule remains excited after it is excited, and that even two molecules can have the same color, can differentiate them. Or the same molecule, whether it's interacting with something else or not interacting with something else, gives you a different lifetime. This is exactly what we picked up, going back to our original problem of amyloids. And we are looking at amyloid oligomers, which are, so amyloids are peptides which get together, clump together, cause Alzheimer's disease in the patient's brain. And we want to look at how the first oligomers form before they become large fibrils. And we wanted to see how those oligomers can interact with things inside the cell. And it was very difficult to look at any interactions until we say, okay, we put very environment sensitive probe on my oligomers, and it goes inside. These are neuronal cells in culture. Goes inside, we'll know where it has gone. And if it's interacting with something, most likely the environment will change and my lifetime will change. You see, the change of lifetime can be actually measured very well on the left side. This is lifetime in nanoseconds, some intensity. You look at decay after you hit it with with some light pulse. How quickly does it decay? You can do the statistics, and this differentiates. Let's say even these magenta from the blue can be differentiated. So you can do this inside the cell, and we built a lifetime imaging microscope and looked at the interactions of amyloid beta oligomers. You can see on the left, they're all bright. They're in astrocytes, they're in cortical neurons, they're in RN46A cells, the neuron cell line. But on the right, you see that the color changes. This color on the right is their lifetime color. Okay, very low lifetime is red, then green, then blue. Blue is very long life. You see, the astrocytes, they have much smaller lifetime than in cortical neurons, which have much smaller lifetime than in HeLa cells, which are somatic cells. And we got a lot of information from this. It's not the forum to talk about it, but if, as I said, it's not always the most expensive, highest resolution that gives you the story. The story here was hiding somewhere else, the interaction story. Okay, so now let's go to the next thing, which is how do we look at this molecular assembly? Lifetime is one, but you want to look at it. Lifetime doesn't tell me whether it's a dimer or the trimer or the tetramer that's interacting with my stuff. I want to know, looking at each oligomer, how big they are. And that comes back to the TIFR microscopy. This is the same image I had shown. I told you that some are a little brighter than the others, which can fool you because there is something called orientation with respect to polarization. So some things may be brighter if they're aligned with the orientation of the excitation polarization, and may look dark. So just because they are bright doesn't mean they're two or three things together. But what you do see, there are places, spots, which are two monomers together, which is a dimer, three monomers together, which is a trimer. And how do I tell if brightness is not a reliable indicator? But I tell by this. I wait for them to photobleach. Same thing I used for in palm. Okay, just wait, keep waiting. And if I follow with high sensitivity each single molecule, if the photobleach in one step, that means only one fluorophore was there. If the photobleach in two steps, that means it was a dimer. If photobleach in three steps is a trimer, four steps is a tetramer. So by looking at these spots individually, I can tell which one is a monomer, which one is a dimer, which one is a tetramer. There's no other way. They're so tightly packed together, nothing will separate. Okay, no high resolution microscopy will be able to tell, other than electron microscopy, which I'm not going to, will be able to tell. Because I can't do electron microscopy, these are on live things, or at least on wet things. So we wanted to know, we asked a harder question that, okay, some are monomers, some are dimers, some are trimers, and they interact with the cell membrane because they come from outside the cell, they have to interact with the cell membrane. How deep do they go? does the trimer go equally deep inside the cell membrane compared to the monomer or the tetramer? This is an even harder question because I'm asking a cell membrane is a 4 nanometer object. How deep has it gone in? So I have to slice half a nanometer where Z different this thing, which is very, very hard to do. Except with photobleaching, it was very easy. If you could think of some other technique, changes the environment. I told you object matters. So suppose you have a bilayer, something is stuck at the top, something has gone a little deep in, something is deeper in, something is deeper, etc. I make my bilayer with lipids which can lengthen the lifetime of the fluorophores. And those lipids have these radicals which lengthen the lifetime of the fluorophores at particular places. Lipids are long chain molecules. Let's say I have 18 hydrocarbons, and one of them would have this radical there. And if it's close to that, my molecule is close to that radical, it will live very long. And I can tell that by photobleaching, the step length of photobleaching. How long does it take to? I can make one bilayer with where the radical is on number 2, C2, right near the surface, or C10 or C16, etc. This is exactly what Arpan, my student, did. These are the doxyl radicals. Can be deep inside, they can be near the surface, they can be somewhere near the neck, somewhere in the middle, etc. And he asked the question, can he differentiate different oligomers and ask how deep they are going? So he had lots of statistics taken for the 4 monomer, trimer, tetramer, and found out that, yes, the most toxic variety has its monomers, look at the red stuff, and its dimers and its trimers going deeper in. They sort of deeper into the membrane compared to some non-toxic variety, which is the green. So again, I'm not going into the science, but it's possible to tell which oligomer of which species is going to what depth with a half a nanometer or less accuracy, depending on the labeling. So again, you need to prepare your sample and you should be able to answer the questions. So I have, 7 more minutes. All right. Now I come to something that I've been doing for, 3 decades nearly. How about label-free imaging? All microscopy till now that I've talked about requires you to put a fluorophore on it. Could be a GFP, could be an organic dye, rhodamine, etc. Even my amyloid beta is organically, is rhodamine label. I have been having this dream of doing label-free imaging, and there is something called photon microscopy that allows me to do it. Okay, so I'll tell you about that. So what is the basis of light excitation? It's not just the intensity. In fact, the intensity doesn't cut it. It's the frequency or the color of the light photon. So this man told us that if you have an energy level, which is this high in energy, and you come in with a violet light, which can give that much energy, your molecules will get excited. Come in with red light, it will never get excited. What he didn't tell us, and a lady, Maria Goepert-Mayer, about 24 years later, told us, yes, even with a red light, you can actually go there if it's intense enough to give it 2 kicks at the same time. These 2 kicks at the same time at a wavelength, which is red, that this molecule doesn't absorb, was the basis of an idea that Watt Webb, the guy I worked with, my postdoctoral advisor, worked with, and he invented something called multiphoton microscopy. So he said, well, the femtosecond lasers, you can give 2 kicks at the same time, and it has certain advantages. One advantage is very clear. You want to go deeper into tissue, you need red light. You can see, this is my flashlight. You see the color is red. Okay? You say, yes, your blood is there, so you see the color of the blood. Actually, the blood doesn't absorb red light, and that's why we see it. Blood absorbs blue heavily and red not so much. So red light goes through our tissue. So if you have to penetrate tissue, if you're doing in vivo imaging or thick tissue imaging, you have to go with red light. But red light doesn't get absorbed by standard fluorophores, so you have to go with multiphoton. It shows another advantage is that the multiphoton depends on intensity. If the intensity is very high, then only it absorbs. and intensity is very high in a focused beam only at the center, not everywhere else. So it tends to excite things only at the center, gives you a 3D imaging resolution automatically by focusing. So this was the first big step after confocal, before all this sub-resolution diffraction barrier thing came in, STED and all. So this is the first nonlinear microscope, and I'll have to go a little faster, and I'll show you that we have had a lot of fun in my lab with molecules such as serotonin. These are molecules which don't have any fluorescence in the visible. They have a fluorescence in the UV. You cannot put UV light because your light cell dies. But you can do 2 photon, which Webb had invented. Then I went there to his lab and I co-invented the 3 photon microscope. And you can put 3 photons of red light, it will go to the UV. It's very simple. 810 nanometers, 3 of the photons means 1/3 of the wavelength, 270 nanometer. 270 nanometer, there are lots of things in our body which will absorb and give out fluorescence, except nobody could do it because if you just put 270 directly, it will burn your tissue. We put 810, and only at the center there's a little bit of burning, and the tissue takes it very well. So I've shown that the neurons can do exocytosis, etc. You can see dopamine, serotonin and dopamine are 2 of the molecules which are intricately related to your happiness, and etc. And our latest thing was to look at how serotonin inside a cell inside a vesicle can affect the vesicular membrane. I'll stop that. I'll not go through this. Don't have any more time. But I'll come to the last bit, which is cancer detection. The guy sitting across the table right here, and another person is helping me build something for cancer. So, a lot of fundamental science I did, and we decided that maybe I should also do something which is quite applied. Okay? So cancer tissue. If I can look at label-free UV imaging, I can do it for cancer tissue also. I don't need to look at neuronal cells. And the way that doctors look at imaging is on the left tissue. So this is actual human cancer tissue, which has been labeled with H and E stains, which are the cancer pathologist's friends. And this is what a cancer pathologist is looking at when he or she has a sample. By looking at the morphology, which it's brought out by the H and staining, it's a 2-dimensional image, and she can tell which part is cancerous, which part is not. This technique hasn't changed in 100 years. It's a 2-dimensional image, these 2 colors, H and E stain. Okay? We said, well, this also means that the whole tissue has to be fixed, stained, sliced, looked at under the microscope. What can multiphoton do? No staining needed, no fixing needed. Slicing is automatic because of the optics. We said we can do it. Okay. So this is on the right is a multiphoton. This is actually a second harmonic generation image, but some variant of nonlinear microscopy with the same tissue that we have a collaboration now to look at. And of course, this is stained. But suppose there was no staining, this image will still come because this comes from nonlinearity in the collagen fibers, etc. So I can, in principle, get the same information or hopefully the same information as they're getting. And I can do that intraoperative in principle. The tissue is dissected out from somebody's tumor. We put it in the microscope right there next to the operation theater, look at it and tell what it can do. Problem is that this pattern is somewhat different from other patterns. I'm getting to the end, I can see. So my friend Swapnil Rane in the Tata Memorial Center didn't know what this pattern could say. They have not been taught to look at the patterns in that way. So we need an AI imaging. Sorry, I can't talk about it too much, but there is our collaboration at CFC UK. And we are now generating a lot of these images using a light sheet kind of multiphoton microscope that Kuldeep and my students, Kuldeep and Ankit, are building. There's the design. There's the sort of first variant. It's not fully built yet. We have some sort of data coming up, but will soon be done. Can do very fast, 100 times faster multiphoton imaging using a sheet, not a point. Okay. And the last bit is something that to do multiphoton with a very low power, using what is called entangled photons. There's a quantum thing. You can generate quantum entangled photon pairs. The problem of two photons, though it's not so damaging, there's still high power needed, milliwatts of power needed, because independent to each other, two photons should come at the same place at the same time. That goes as square of the intensity. In entangled photons, one drags the other. They are entangled. So I do linear with intensity, and there is a way to do microwatt level multiphoton imaging. There is still in the design stage. In fact, we are looking for funding for this. If we get the funding, there'll be fun building. Okay, let me just end by thanking the people who are working with me here in BITS, Kuldeep and Ankit on the left. The other guys who have contributed to the last parts of my work in TIFR, where I spent 27 years, Dev Shankar and Shankho, and all my collaborators, including my STFC collaborator team, others, and all my other students. And funding comes from BAE and also BITS Pilani, Hyderabad. And I'm looking for PhD applicants. Okay, thank you very much. I'm done.
Thank you so much, Sudipta. It was really exciting to see your work. Especially, I'm very curious to hear more on the last bit that you were talking. Maybe I think I will hopefully catch you in person in BMC to discuss on that. So now I'll hand over the stage to Dr. Nihit to take up the Q&A.
Okay,
Nihit,
thank
over to you.
Thank you, Lakshmi, and thank you, Sudipta, for this inspiring talk. To all the participants, if you want to ask questions, you can please type them in the Q&A section at the bottom of your screen. And I will just ask them one by one to Sudipta, and he can take them in that order. So we already have 2 questions from the Q&A, and I will start with the first one. It is about the min-flux setup. So the question is, how does the molecule under observation is studied in min-flux when the same is not being illuminated?
So what you get to know is only about the position. Okay. So what happens is that you have a ring. Imagine a ring and a ring of light around a lady who is dancing. And actually, you don't want the audience to see her dancing. So what she does is she is dancing around on the stage. She comes under the ring of light, the sort of a annulus of light, and briefly you see her. So you move your annulus so that she is again at the center where there is darkness. And she moves somewhere else, and a little bit you see her, then you move it again, and she's at the center. So thereby you're tracking a single molecule, and you know the position, because the moment she leaves the center, a little bit, she becomes somewhat bright. The brightness goes up, 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 and goes down again in this donut thing. And you always know the position. And the position information can be for a fixed tissue, just the molecule where it is, or for a tissue where the molecule is moving. You can track a single molecule in space. So it's position information. Even though you're not looking at it, you're actually looking at it sometimes. And you are moving the thing so that it becomes invisible.
Thank you, Dr. Sudipta. The second question is about multiphoton microscopy. And the question is, can we get resolution of multiphoton microscopy by using less number of photons? So,
okay. So multiphoton, so that's the last part. Multiphoton microscope, unfortunately, goes as square of the intensity because 2 photons independently have to arrive at the same time. Each photon, the probability goes as intensity, so its intensity is square. Which means, suppose you have some molecule which is nice and bright, let's say at 1 milliwatt. If you go to 1 microwatt power, the signal doesn't go down by a factor of 10 to the power 3, goes down by a factor of 10 to the power 6. So you lose the signal the moment you reduce the power. It's quadratic. The only way that has been suggested and now beginning to be shown in some labs, my friend Ted Goodson's lab in Michigan, is using quantum entangled photon pairs where the intensity dependence is linear. So you go down 10 times, you lose only 10, not 100, but it's still multiphoton. So all the other characteristics are there. All our other advantages are there. Except right now, you only work at a very low light levels, and the fluxes that you can put in for entangled pairs are very low. So it takes 2 hours to take an image. And we have some ideas that we have recently proposed to the funding agency that I think you can do it 100 times better. So it will still be a long way before this becomes a very usable instrument. But it's a lot of fun because there are a lot of other things that entangle photon pairs. These are quantum light, not classical light, they can do. So exciting things.
Thank you, Sudipta. The third question is about the photo bleaching experiments. So the question is, don't you think fluorophores which enter into the dark state or get quenched by other conditions can interfere with the results?
No, the fluorophores, these are permanent darkness. What happens is then oxidation. Once the thing oxidizes, so you see these molecules which are fluorescent, they all have some kind of a ring structure. The ring breaks because it oxidizes. And there is no way for it to put it back, so it's gone. And for fluorescent microscopies is as good as not existing. So it cannot influence the results. Not in any direct way anyway. Okay, it's still there, physically there. It's just one part of one ring broken. And so you can pretty much neglect the effect of that, the others. But you can count. One breaks, other breaks. It's like your Diwali lights. Very cheap Diwali lights. By the time you put them up, the 100 lights and you count is 98 and come back after 2 minutes is actually 96 because some have gone off. So it's just like that. But here we take advantage.
Thank you, Sudipta. Another question is about the parameters for multiphoton microscope. So what are the usual wavelengths, pulse duration, and powers, average powers of the laser for multiphoton microscopy?
So the pulse duration is actually typically given by the laser that you have. It's about less than 100 femtoseconds, about 100 femtoseconds. And the powers that you need depends on the fluorophore that you have. A couple of milliwatts is enough to drive rhodamine to saturation at the right wavelength. Just a couple of milliwatts. But most molecules will get saturated 4 or 5 milliwatts. There's no point putting more than that at the sample. But 3 photon takes about 10 times more than that, 20 to 30 milliwatts. But still, as I showed, 3 photon, because the wavelength is non-damaging, the cells are rather happy. They do exocytosis for hours under 3 photon imaging. One thing that as facility managers or as users you must be looking at, there are lots of things outside of the laser that will change your pulse width. So there is something called dispersion compensation that many of the lasers these days come with it. You should test it. You should make it go this way and that way. Get the brightest image for the same power. Keep the power low, move the slide things and get the brightest image. So that you must, in 2 photon, the pulse width is inversely linearly proportional to the signal intensity. In 3 photon is inverse quadratic with the intensity. So you must be, in 3 photon at least, you have to be very careful about the pulse width.
Thank you, Sudipta. Another question on 2 photon microscopy. The question is, how does 2 photon excitation helps to do imaging without labeling or eliminating the need for dyes?
Okay, so I had to run too quickly through it. So many of our molecules, our means native molecules, which are not fluorophores per se, are actually fluorescent, but they absorb in the UV. We don't have fluorescent molecules normally which absorb in the visible. We do absorb in the visible. I'm quite brown, but that's not fluorescent. So the things which are fluorescent are protein components such as tryptophan. Almost all proteins will have tryptophan, or other molecules such as NAD, FAD, NADH, FADH, serotonin, dopamine. They're very important molecules. NADH reports on the metabolic state, and it's very easy to image in live cells, except you have to go UV. If you put UV on your sample, the whole light has to go through and excites everything in its path and destroys everything. If you put multiphoton, because I'm going 3 photon or sometimes 2 photon, then unless you are right at the focus, nothing else is getting destroyed or excited. So by the time you're done with scanning, the thing is still alive. While if you do the same thing with UV confocal, the thing will be dead. And you also will not be able to penetrate because red light can penetrate. Scattering is much less, as they showed you with the flashlight. UV doesn't penetrate. So it's a killer and also cannot penetrate. So the only way to do is multiphoton. In fact, I would say this is one of the major advantages of multiphoton that is underutilized because people are a little scared of looking into these too much. But look at NADH. Look at some of the calcium the reporters indoor. They're fantastic, but they're in the UV or near UV. So you should use multiphoton.
Thanks, Sudipta. There is another question about the imaging techniques for A-beta oligomers. So what are the imaging techniques for understanding interaction of A-beta oligomers with membrane? And can Raman spectroscopy be used or Raman imaging be used for this?
Very good question. Yeah, we do Raman imaging also. We have built a Raman confocal microscope, line scanning Raman confocal to actually look at these. Unfortunately, Raman is a very a low signal intensity technique. So if you have these molecules at nanomolar levels, you typically won't, or micromolar even, typically won't see it in Raman. However, 2015, my student Devanjan found a way around it. He wrapped a membrane around a gold nanoparticle. The gold nanoparticle creates something called plasmons when they're excited. And these plasmons actually give a tremendous amount of amplification to the Raman cross-section, Raman intensity. And that is about 10 to the power 4 or so. With that, he could easily do 1 micromolar amyloid beta molecule interacting with membranes. So yeah, there are ways to do it, but Raman by itself, standard Raman, is very weak.
Okay, thank you, Sudipta, for this answer. Another question about multiphoton microscopy. So in multiphoton microscopy, is it possible to differentiate if 2 photons or 3 photon between 2 photons and 3 photon regions in an unstained sample?
It is. Again, a very good question. And it's a very easy answer, which is you go down in your power, laser power by factor of 2. If it's 2 photon, your signal will go down by factor of 4. If it's 3 photon, it will go down by factor of 8. 2 square or 2 cube. So it's easy to tell.
Thank you. Another question about 2 photon excitation. So even if a molecule is excited by 2 photon excitation, how do we make sure that it emits fluorescence so that it can be studied? So,
sorry, say that again, please. I didn't quite get it.
Yeah, so the question is, how do we make sure that there is fluorescence coming out of a molecule in 2 photon microscopy?
Well, short answer is in 1 photon, if you don't see any fluorescence, then you won't see any fluorescence in 2 photon either. Take the molecule, whatever the reporter is, either is a fluorescent protein or a dye, put it in a fluorimeter. And if it doesn't have fluorescence, it doesn't have fluorescence. The 2 photon is just a way to excite it in a different way. But the fluorescence quantum efficiency is something that if it's nearly 0 for a molecule, then you can do microscopy with it.
Thank you for this answer. So there is another question, a slightly detailed one. Given the spatio-temporal resolution requirements and depth limitations inherent to different imaging modalities, how would you compare the strengths and limitations of confocal laser scanning microscopy versus turf microscopy in quantitatively capturing early nucleation events and condensate maturation during LLPS of intrinsically disordered proteins at subcellular resolution?
Very good question. So if your LLPS or the aggregates are forming right at the cover slip, always go for TUF. It's much faster. It has high Z resolution, and its XY resolution is just as good as the confocal. In fact, a former student of mine who is a faculty in TIFR Hyderabad now, Kanchan Garai, has done a lot of work with a TUF microscope looking at nucleation and condensation, also together in a collaboration with Thomas Notes. So yeah, so the answer is if it comes to the bottom, then there's no problem. Doesn't come to the bottom, you want to look at the cell somewhere else away from the cover slip, then there are very few options left. You can do TARS and you can do light sheet, but usually you won't do light sheet because that's much worse resolution. You'll probably do confocal. You don't have really many other choices.
Okay. Thank you, Sudipta, for this answer. Are there further questions from the participants? They can please type them in the Q&A section. For now, I don't see more questions in the Q&A. Perhaps I can ask one quick question from my side.
Sure.
So I was wondering about the last part of your talk where you talked about light sheet combining it with multiphoton imaging. So usually with light sheet, you want to be very gentle in terms of the intensity. But with multiphoton, we typically use much higher laser powers. So how do you sort of bring these two together in this multiphoton light sheet microscope?
Yeah, so multiphoton, the higher powers actually are mitigated by the wavelength, because you're typically putting, let's say, 800 nanometers or so, and it's much less damaging. And that's why multiphoton many times is much less toxic, phototoxic to cells than single photon, even though the multiphoton takes at least a couple of milliwatts of power, while single photon will take 100 microwatts of power, 20 times less. So, however, it also depends on the sample. If the sample has residual absorbance at 700 to 800 nanometers, then it will heat up with the multiphoton light and it will probably cause a lot of damage. So, yeah, so that's the answer, that you really have to test it. So in light sheet, of course, you have to put a lot of light. And the point I made before, that if you make one spot into two spots, your signal goes down by a factor of 4, okay, because you half the power each. So that's the disadvantage of multiphoton light sheet. So you're playing with multiphoton light sheet or line scan, and I think my students are veering towards a line which will get scanned. We can still do the recording at 50 to 100 hertz per frame, and that seems to be working well. But to do a proper line as a this thing, okay. So the advantage of this one line and looking at it perpendicular is the same power goes through. Okay, and you scan this line and you put it on a camera. So it takes, on an average, less power than a line projected on to the sample. But the line projected on the sample lets you use the highest NA that you have and gives you a much higher resolution. So it's really a give and take. But none of them, all of them are obviously much higher power than your single photon light sheet. I'm talking about 100, 200 milliwatts at the back aperture of the object.
Right. Thank you. Thank you for the answer.
Sure.
There is a question by Venkateshan. So Venkateshan, can you please unmute yourself and ask?
So nice talk, Sudipta.
Thank you, Venkateshan.
So I want to ask about the when you talk about palm and storm, you did do it in the turf mode, right?
Yeah.
Yeah, but if you want, let's say you want to go deeper into your sample, let's say if we want to go at the nucleus or something, do you think you can combine light sheet with storm or palm?
What they do, you can. There is nothing in the physics that doesn't that bars you from doing that. And palm people typically will go not complete sort of total internal reflection, but as a what they call high-low. So they do it. They do it because the resolution, the thickness you would not get, but you will get. We will be able to do palmers.
Okay. Thanks, Sudipta. There are two more questions in the Q&A. The first one is, can a wavelength which is not absorbed by the sample damage its fluorescence properties?
Not really. I mean, in 2-photon, we choose a wavelength which is not absorbed by the sample. And except, of course, as I said, at the focus, you cause a 2-photon transition. So therefore, it can damage. It's a non-linear transition. But in the linear regime of power, if it's not at the focus, then it shouldn't damage. It's always, if you see damage, it's always because there is some residual absorption at that level.
Thank you. So one more question is, I think it's also in the context of multiphoton microscopy. How is the laser mode decided?
Laser mode, are you talking about, so this gets to technical things, are you talking about longitudinal modes or the mode locking, which is a temporal mode locking? I don't know what the person has in mind, but if you're talking about spatial mode, transverse mode, then you need to have TEM00, which is called basically a quasi-Gaussian thing or flat. And having higher modes, which will look like a double lobe, TM01 or something, would not do it because your intensity is getting distributed. And for the same reason, I said you put two beams instead of one, you lose your quadratically the signal. So it has to be spatially a TEM00 kind of. I think that was the answer. There are many more types of modes in a laser. So I don't know the question.
So Sarika, would you like to clarify your question, or otherwise we can move on? So please type in the Q&A if you want to clarify. Otherwise, we can move on. Okay, I think that was her question. So
Okay, good.
That's fine. Okay, I think we are not seeing more questions in the Q&A.
Good.
Okay, there is one more, sorry. Just came up. So the question is, can you explain how quantum light is generated?
So typically it's generated in nonlinear crystals in using the process called parametric down conversion. This is an old technique. There's nothing new in quantum light. Parametric down conversion, where something with energy h nu gives out two photons, h nu 1 and h nu 2, I mean nu 1 and nu 2, whose energies add up to the original photon. But these two, when they're generated together, they're entangled. Could be time energy entanglement, could be polarization entanglement, but they're entangled because they were created together. Lot of conservation laws, the polarization, the momentum, the energy, they all have to be conserved. Which was there for the first photon should be there for this pair of photons. So they are sort of entangled.
Thank you, Dr. Sudipta. So in the interest of time, and also we don't have further questions in the Q&A, we can probably close this session. So I would like to thank Dr. Sudipta Maiti for this great talk and also for answering all the questions. And I will now hand over to Suganya for conclusion of the session. Thank you, Sudipta.
Most welcome and really enjoyed it.
Or if Suganya is...
Sorry. Thank you, Sudipta, for the great talk. I think everyone loved the session.
Most welcome.
Mahesh has something to say about the recording and conclude it, I guess.
Thank you, Dr. Sudipta, for your wonderful talk during the webinar. We truly appreciate the time and insights you shared with the IBI community, from the fundamentals of light microscopy to advanced techniques such as stirred, minflex, single molecule localization microscopy, light sheet, film, multiphoton, label-free, whatnot you covered. You have presented the overview of it. And the question and answer session was especially engaging and thought-provoking as well, reflecting the enthusiasm of our participants. And thanks to everyone for making this first webinar successful. I would say kickstart from IBI community. And the announcement is that the recorded session will be available soon on the IBI YouTube handle, official handle. It's like India Imaging. So at YouTube, you just need to go and @ India Bioimaging. The recorded sessions will be available soon on the IBI YouTube channel. Stay tuned to IBI for more events, updates, and exciting learning opportunities. Thank you very much.